Welcome to the Curious Voyager. It's lovely to have you here tonight, wherever you are. Maybe you're lying in the dark with the blankets pulled up to your chin. Maybe there's a lamp still on somewhere across the room, throwing a soft little pool of light on the ceiling. Maybe you're on a train, or a couch, or the floor of a room that isn't quite yours yet. Wherever you are, whatever the hour where you're listening from, you've arrived at exactly the right place. There's nothing you need to do now, nothing to solve, nothing to hold on to. You can let your eyes close whenever they'd like to. And before we begin to drift, just a small and gentle thing. If you enjoy these slow journeys into the strange and beautiful corners of the world, a quiet like and a subscribe really do help this sleepy little channel keep going. Small creators like me lean on that kind of support more than you might think. And to those of you who are already here, already part of this, already returning night after night, thank you. Truly, it means more than I can say. So tell me, if you feel like it, where in the world are you listening from tonight, and what time is it in your corner of the dark? I always love to imagine all of you, scattered across the world, drifting off under the same strange sky. Now, I'll make you my usual promise. I'll try very hard not to make this so interesting that it keeps you awake. But if it does, well, at least you'll have learned something lovely on your way to sleep. A fair trade, I think. We're going to move slowly tonight, softly, one idea at a time, with plenty of room to breathe between them. If you drift off before the end, that's perfectly fine. The ideas will still be here. They're patient. They'll wait for you. So settle in, let your shoulders drop away from your ears. And let me tell you about something that a group of very patient people did in a quiet laboratory in the city of Vienna. In the year 2019, in a machine about 2 meters long, a single molecule was made to do something that should be impossible. Something that, by every rule your everyday life has ever taught you, simply cannot happen. This molecule, made of roughly 2,000 atoms, was sent down a path. And at the same time, it was sent down another path. Not one, then the other. Not the first molecule going left and a second going right. One molecule, two paths, at once. It travelled both ways through the machine as a single blurred possibility of itself, and only settled into one definite answer at the very end. Let that sit for a moment. 2,000 atoms. A real physical object, the kind of thing that has a weight and a shape and a name. And it was, in a measurable sense, in two places at the same time. This is the heaviest object that human beings have ever caught, living in two states at once. The current record holder. The champion, if you like, of a very quiet and very strange competition that has been going on for decades. The molecule was a special kind, built to order, called an oligoporphyrin. You don't need to remember that word. It's just a large, carefully designed molecule stitched together by chemists specifically so it could survive this journey. And its mass, the amount of matter packed into it, was more than 25,000 daltons. A dalton is simply the unit scientists use to weigh the very small, roughly the weight of a single hydrogen atom. So 25,000 daltons means this thing weighed about as much as 25,000 of the lightest atoms, all bundled together into one object. The people who did this were Yaakov Fein, Markus Arndt, and their colleagues at the University of Vienna, and they published it in a journal called Nature Physics. They titled their paper, with a kind of quiet triumph, Quantum Superposition of Molecules Beyond 25 Kilodaltons. The machine they used had a lovely, unwieldy name too. The Long Baseline Universal Matter Wave Interferometer. LUMI for short. a 2-meter tube of the most careful emptiness ever engineered. Now here is the part that I find almost impossibly beautiful, the part that I hope you'll carry down into sleep with you. To make an object travel 2 paths at once, physicists rely on a strange truth about the world. Everything, every object, no matter how solid it feels, is also, in some deep sense, a wave, a spread-out ripple of possibility. And to split that object across 2 paths, you split its wave. But the wave that belonged to this molecule was tiny, almost unbelievably tiny. It was on the order of 53 femtometers. A femtometer is a distance so small it barely makes sense to say out loud. It's a millionth of a billionth of a meter. And here is the strange thing. That wave, the ripple that carried this molecule down both paths, was about 1,000 times smaller than the molecule itself. Smaller than a single atom inside it. Smaller even than a proton, one of the tiny specks that sit at the heart of every atom. Think about that gently. The object was delocalized, spread across 2 paths, using a wave far, far smaller than the object doing the traveling. It's a little like being carried across a canyon on a thread thinner than the hair on your arm. It shouldn't hold. It shouldn't work. And yet, in that quiet Viennese machine, it did. I want you to just picture it, softly, the way you'd picture a scene in a dream. A long silver tube in a darkened room. Inside it, a near-perfect emptiness, emptier than the space between planets. And through that emptiness, a molecule drifting, no longer quite a single thing, spread out like a whisper across 2 possible journeys, riding a wave smaller than the smallest thing you've ever heard named. Held there, in 2 states at once, for just long enough to prove it happened. That's the image. That's the prize. That's what a small group of patient humans managed to do. But I've gotten ahead of myself, the way one does when something is exciting. Let me go back. Let me tell you where this whole strange idea actually begins, and why every gram of weight makes it so unbelievably hard. The story really starts in the year 1924 with a French physicist named Louis de Broglie. De Broglie proposed something that sounded at the time like the invention of a dreamer. He said that all matter, everything, has a wavelength. Not just light, not just the strange, ghostly stuff of the very small. Everything, you have a wavelength. This blanket has a wavelength. The cup of tea cooling on your nightstand has a wavelength. And he even gave a formula for it, one clean little equation that will quietly become the villain of tonight's whole story. He said the wavelength equals Hish divided by mv. Let me decode that for you, gently, because I never want to leave a term sitting there like a stone. The Hish is Planck's constant, which is just a very small fixed number that shows up whenever you talk about the quantum world. Think of it as a tiny, unchanging seed at the heart of the equation. The m is mass, how heavy the object is, and the v is velocity, how fast it's moving. Together, m times v is called momentum, which you can think of as how much oomph an object has, how hard it would be to stop. So the equation says the wavelength, the size of the ripple, is that tiny seed number divided by the object's momentum. And here's the crucial thing, the thing that makes this whole endeavour so punishing. The bigger the momentum, the smaller the wave. Add more mass, and you divide by a bigger number, and the wave shrinks. Move faster, and the wave shrinks again. So a heavy object, or a fast one, has a wave so absurdly small you could never hope to see it. A tossed pebble has a wavelength trillions upon trillions of times smaller than the pebble. That's why you never see a baseball go two ways at once. Its wave is real, de Broglie insisted, but it's so vanishingly tiny that nothing in the world could ever reveal it. This is the spine of everything. This is why the race to hold ever heavier objects in two states at once is so brutally slow. Every single atom you add to your molecule makes it heavier. And every bit of heaviness shrinks the wave you're desperately trying to reveal. The physicists in Vienna weren't just fighting engineering problems. They were fighting a fundamental law of the universe, one clean equation from 1924 that says, over and over, the bigger you go, the smaller your wave gets, and the harder it becomes to catch it living two lives at once. To hold a 25,000 Dalton molecule in superposition, they had to reveal a wave smaller than a proton. That's what de Broglie's equation demanded of them, and somehow they paid the price. Now you may already be thinking of a certain cat. Almost everyone who hears about two states at once thinks of it eventually, and it's worth telling that story properly, because it's usually told all wrong, and the truth is far more interesting. In the year 1935, another physicist, an Austrian named Erwin Schrödinger, wrote about a cat. He published it in a German science journal, and he described a rather grim little scenario. Imagine, he said, a cat sealed in a box. Inside the box is a single atom of a radioactive substance, the kind of atom that might decay at any moment, or might not. And connected to that atom is a device that, if the atom decays, releases something that would harm the cat. Now, the strange rules of the quantum world say that until you check, the atom is in a blur of both possibilities, decayed and not decayed, at the same time. And so, Schrödinger argued, if you follow that logic all the way up, the cat too must be in a blur. Both states at once, until you open the box and look. But here is the part that gets lost. Schrödinger did not propose this because he believed it. He proposed it because he thought it was absurd. It was a joke, in a sense, a piece of mockery. He was trying to ridicule the idea that the strangeness of the very small could ever climb up and infect something as large and real and warm as a living cat. He meant it as a reductio ad absurdum, a way of saying, look how ridiculous this gets if you take it seriously. Look how obviously wrong it must be. The cat was never a goal. It was a punchline, a warning sign. And this is the quiet, delicious irony at the heart of tonight's journey. The very thing Schrödinger held up as impossible, as self-evidently ridiculous, is exactly the thing that physicists have spent the decades since patiently trying to build. Not a cat, of course, not a living creature in a box, but the principle behind it, a real, tangible object held genuinely in two states at once. Schrödinger drew a line in the sand and said, surely reality stops here, surely the strangeness cannot cross this line. And ever since, people in quiet laboratories have been gently, carefully, molecule by molecule, walking right up to that line and pushing it a little further out. That 25,000 Dalton molecule in Vienna is, in a sense, the closest anyone has yet come to building the thing Schrödinger swore could never be built. He would, I think, have been astonished. Perhaps a little delighted. Perhaps a little unsettled, as, honestly, are we all. In those same 1935 papers, by the way, Schrödinger also gave us another word we'll return to later. Entanglement. In his native German, Verschränkung, it describes how two quantum objects can become so deeply linked that you can no longer fully describe one without the other. We'll come back to that idea, softly, further along the road. For now, just let the word rest in the back of your mind like a small candle. Entanglement. We'll return to it. Now, I want to be very careful about something, because it matters for what makes tonight's story different from the version you may have half heard before. When most people talk about objects being in two places at once, they reach immediately for a famous image: the double slit. You may have seen it, tiny particles fired at a barrier with two openings in it. And instead of making two neat piles on the far side, they build up a striped pattern, a pattern that only makes sense if each particle went through both slits at once, as a wave. And there's a beautiful film of it, made by a physicist named Akira Tonomura in the year 1989, where you can actually watch single electrons arrive one at a time, dot by dot, seemingly random at first, until slowly, magically, the stripes of a wave pattern assemble themselves out of the scattered points. It's a gorgeous thing to see. But that is not our story tonight. That's the picture on the postcard, the one everyone already has. Electrons are unimaginably light. Of course, they behave like waves. Their de Broglie wavelengths are relatively enormous, revealing the wave nature of an electron, while a triumph in its own time is the gentle foothills of this mountain. What we're climbing tonight is something else entirely. We're not talking about a single feather-light electron. We're talking about an object of 2,000 atoms. A molecule you could, in principle, weigh, a molecule with real chemical bulk. Getting that to go two ways at once is not the foothills, it's the sheer face of the cliff. So I'll gently set the double slit aside, keep it there in the background as the thing that first showed us matter can be a wave, and turn our attention to the far harder, far stranger art of doing it with something heavy. Because that is the whole promise of tonight. Not the well-worn tale of the electron, but the patient, decades-long human effort to take that same wave strangeness and drag it upward, atom by atom, toward the world of things you could almost hold, toward the border where the quantum world ends and your ordinary, solid, reliable world begins. Nobody yet knows exactly where that border is. Nobody has found the wall, and the search for it is one of the most beautiful and humble stories in all of science. Here's what I'd like you to feel as you drift. This isn't a story about paradox meant to unsettle you. It isn't the anxious, dizzying version where reality is broken and nothing means anything. It's the opposite. It's a story about patience, about a small number of careful, curious people working in quiet rooms with impossibly delicate machines, gently asking the universe a question and waiting a very long time for the answer. Molecule by molecule, year by year, pushing the edge of the known just a little further into the dark. There's something deeply restful in that, I think. The universe is strange, yes, but it's a strangeness being explored with care by people not so different from you, who also, at the end of a long day, have to sleep. So let's stay with the molecule for a while longer, because the how of it is as lovely as the what. To make that oligoporphyrin travel two paths at once, the physicists in Vienna could not simply fire it at two slits, the way you would an electron. A molecule of 2,000 atoms is far too heavy, far too slow, and, in a sense, far too messy. Its wave is smaller than a proton. Remember, there is no ordinary slit fine enough, no ordinary barrier that could split something so vanishingly small. They needed a machine of extraordinary subtlety, a machine that could take a whole beam of these fat, slow molecules and coax each one into interfering with itself, into being a wave, without needing a single perfect source or a single perfect slit. And it had to be empty, emptier than you can easily imagine. Because the enemy of this whole endeavour, the thing that ruins it faster than anything else, is contact with the outside world. A single stray molecule of air drifting in and bumping into your delicate superposition is enough to collapse it, to force it to choose one path, to end the two-ness before you can catch it. So the inside of that machine was an ultra-high vacuum, a near-perfect nothing, with almost no gas at all to interfere. A hollow silence more complete than the space between the stars. And more than that, the molecules themselves had to be kept cool. Because here is a subtle and gorgeous problem, one I want to unfold slowly for you. A warm molecule glows, not with light you could see, but with heat, with a faint infrared shimmer, the way any warm thing radiates a little of its warmth away. And when a molecule that's trying to be in two places at once emits a little photon of heat, that photon carries away information. It carries, in effect, a tiny message about where the molecule is. And the universe, having received that message, having been told the molecule's position, gently forces the molecule to commit. The two-ness collapses. The molecule betrays itself, gives away its own location by glowing, and the superposition is lost. Isn't that strange and lovely? A hot molecule cannot keep its own secret. Its own warmth whispers where it is, and the whisper is enough to end the magic. So to hold that molecule in two states, the physicists had to keep it cold enough, and quiet enough, and alone enough, that it never gave itself away, that it never emitted the tiny glow that would collapse it back into one ordinary thing in one ordinary place. Ultra-high vacuum, low internal temperature, isolation from every stray field, a cocoon of perfect solitude, engineered so that a single molecule could keep its impossible secret just long enough to prove it was true. This is why the record climbs so painfully slowly. Every atom you add to your molecule doesn't just shrink its wave, the way de Broglie's equation demands. It also makes the molecule a better antenna, a bigger, warmer, more talkative object, more likely to bump into something, more likely to glow, more likely to leak its position out into the world and collapse. The bigger you go, the harder the universe works to catch you at it, to measure you, to drag you back into the ordinary. It's as if reality itself resists being caught in two minds, and resists harder the larger the thing you're trying to split. And so the people who do this work must fight for every single Dalton. Every added atom is a small war against the tendency of large things to be, stubbornly, in only one place. I'll come back in a while to the beautiful and unresolved question of why that is, why large things insist on being in one place. Whether it's just this leaking, this whispering to the environment that we can, in principle, always prevent with a good enough vacuum and a cold enough molecule. Or whether there's something deeper, something built into the fabric of reality itself, a hidden rule that says beyond a certain size the two-ness simply cannot survive, no matter how perfectly you isolate the object. That question, as it happens, leads us to a mountain in Italy and to some physicists who went deep underground to watch for a glow that might tell them the answer. But that's further down the road. We'll get there slowly. For now, I just want you to hold the picture of that machine. 2 meters of engineered emptiness, colder and quieter and more alone inside than almost anywhere in the universe. And a single molecule, 2,000 atoms strong, drifting through it as a wave smaller than a proton, spread across 2 paths at once, keeping its impossible secret just long enough It helps, I think, to understand that these molecules don't move through the machine the way you might picture a marble rolling down a groove. They arrive as a beam, a faint stream of these carefully built molecules drifting forward through the vacuum. And the machine's job is to take that beam and, without ever pinning down any single molecule, gently divide each one's wave so that it explores more than one route through the apparatus and then brings those routes back together at the end. When the routes recombine, they either reinforce each other or cancel each other out, depending on the delicate details of the wave, and this leaves a faint striped pattern of where the molecules are more and less likely to land. That pattern, those quiet stripes, is the fingerprint of 2ness. It's the proof. It's the only way to know, after the fact, that each molecule really did travel more than one path, because no single molecule ever announces it directly. You cannot watch it split. You can only see, in the pattern left by many molecules, the unmistakable signature of a wave, of an object that was, however briefly, more than one possibility at once. And every time that pattern appears, faint and striped on the detector, it's a small miracle earned through enormous care. It means the vacuum held. It means the molecules stayed cool enough not to glow their positions away. It means, for a fraction of a second, an object of 2,000 atoms genuinely lived two lives, and nobody, nothing, no stray photon or drifting air molecule, caught it in the act quite quickly enough to stop it. There's a number that captures just how humbling and how astonishing this all is, and I want to give it to you gently, because it's the kind of fact that puts the whole thing into a soft and proper perspective. That record-breaking molecule, 25,000 daltons, the heaviest object ever held in two states at once. By everyday standards, it is still fantastically, almost comically small. It weighs about 4 times 10 to the minus 23 of a kilogram. And to put that in terms you can feel, it is roughly 10,000 billion times lighter than a common housefly. Say that softly to yourself. The heaviest thing ever caught in two places at once is 10,000 billion times lighter than a fly you'd wave away without a thought. That is the current frontier. That is as far as human beings have managed to push the strangeness, up from the world of single electrons into the world of large molecules. And it's still unimaginably smaller than the smallest thing you could ever see. Which means your world, the world of blankets and teacups and the soft weight of your own body against the bed, stays whole, stays ordinary, stays reliably in one place at a time. The strangeness is real, but it lives, for now, far below the threshold of anything you'll ever hold. And there's a deep comfort in that, I think, as you lie there in the dark. The universe is stranger than you knew. But the strangeness is gentle and small and very far away from the solid ground of your own quiet night. Now let me take you back once more, back down the ladder, to see how we ever climbed this high in the first place. Because 25,000 daltons was not the beginning. It was the top rung, so far, of a slow and patient climb that started with a much smaller and rather more famous molecule, a little sphere of carbon that some people think looks like a tiny soccer ball. To understand how remarkable the record really is, you have to see how far the climbers came to reach it and how much each single step cost them. And that climb, that beautiful, punishing 20-year climb from a ball of 60 carbon atoms all the way up to 2,000, is where we'll wander next. It is a beautiful thing, this climb. Slow, yes, almost absurdly slow, but patient and real and very deliberate. And it starts in Vienna, in the final year of the 20th century, with a molecule that most chemists at the time thought of as a laboratory curiosity rather than a tool. A little hollow sphere made of nothing but carbon atoms, 60 of them, arranged in a pattern of pentagons and hexagons that made it look, if you could see it, uncannily like the ball a child might kick across a garden on a summer afternoon. 60 carbon atoms. Carbon, the same stuff that makes graphite, that makes diamonds, that makes the ink this story might once have been printed in. 60 of them locked into a single, stable, perfectly symmetric cage, just under a nanometer across. Chemists had been studying this molecule since the mid-1980s, and they had given it an affectionate nickname. They called it a buckyball. Formerly, it was C60, or, if you wanted to be more precise, a fullerene, a term that honoured the architect Buckminster Fuller, whose geodesic dome designs the molecule's cage-like shape echoed so neatly. It had been discovered to exist in interstellar space. It had won its discoverers a Nobel Prize. It was, by the standards of molecular chemistry, quite famous. But in 1999, a team of physicists at the University of Vienna decided to ask a very different kind of question about it. Not what properties it had, not how it bonded, not how to synthesize it in larger quantities. They wanted to know something stranger than any of that. They wanted to know whether a C60 molecule, all 60 atoms of it, its entire hollow carbon sphere, could be made to behave like a wave. The team was led by Markus Arndt, working with Anton Zeilinger, who was already one of the most celebrated quantum physicists alive. And what they did, late in 1999, was this. They aimed a beam of C60 molecules at a very finely machined diffraction grating, a thin silicon nitride membrane etched with parallel slits, each slit just a few dozen nanometers wide, spaced about 100 nanometers apart. The molecules in the beam were travelling at a few hundred meters per second, rather hotter than comfortable, and they were individual spheres of carbon arrayed in a beam so thin and faint it barely deserved the name. And one by one, those spheres passed through the grating. And on the other side, measured by a scanning ionizing detector, the molecules arrived not in a pattern that said these particles went through specific slits and landed accordingly. They arrived in a pattern that said something else entirely. They arrived in bands of high density and low density, alternating rhythmically, the unmistakable signature of interference. One wave passing through many openings, overlapping with itself, constructing a bright fringe here, cancelling to nothing there. The fullerene, all 60 carbon atoms of it, had travelled as a wave. It had taken all the paths at once, as quantum mechanics had always said it should. And then it had revealed itself as a single dot when it arrived. The result was published in Nature in 1999. It did not, for the most part, make the front pages of newspapers. But inside physics, it was immediately recognized as something significant. Because C60 is not an electron. It is not a photon. It is not a single atom, the kind of object that physicists had already coaxed into wave behavior over many decades. C60 is a real molecule. 720 daltons, that is its mass in atomic mass units, where a single hydrogen atom is 1 dalton and a proton is very nearly 1 dalton. 720 protons worth of matter, locked into a rigid sphere, warm enough to be practically glowing by quantum standards, and still managing to interfere with itself as though it were nothing more substantial than a ripple on water. That was the first rung. 720 daltons. And the climbers rested there for just a moment, looked upward, and then began to plan the next step. It came 4 years later, in 2003. The Vienna group had spent those intervening years refining their techniques, building a cleaner apparatus, improving their detectors, and thinking very carefully about which molecules to try next. What they chose was, in a way, a logical extension. Fluorofullerene, C60F48, the same buckyball cage now studded with 48 fluorine atoms hanging off its outer surface, heavier, messier, more complex, its mass roughly 1,600 daltons, more than twice as heavy as the original buckyball. And they interfered it. They also interfered tetraphenylporphyrin in that period, a flat, organic molecule that is a close chemical relative of the compound at the center of the hemoglobin in your blood right now, the molecule that carries oxygen through every tissue in your body. These were no longer simple, symmetric spheres. These were genuine organic molecules of some chemical complexity, and they too produced interference fringes when passed through the grating. 1,600 daltons. Still tiny, invisible by any measure you could apply in a kitchen or a garden, but more than twice the buckyball. And the pattern was holding. The wave behavior was there. And so the group looked upward again and kept climbing. The next significant step came a few years later, and it was a larger one. By around 2011 and 2012, Stefan Gerlich and Markus Arndt and their colleagues had pushed the frontier considerably further. The molecules they were now working with were far more elaborate constructions, functionalized derivatives of a class of compounds called phthalocyanines, large flat ring structures with additional chemical groups attached to their edges, purpose-built to be as heavy as possible while still remaining coherent enough to interfere. The molecule that finally set the record in that phase had around 430 atoms and a mass of roughly 6,900 daltons, nearly 10 times heavier than the original buckyball, still invisible to the naked eye, still smaller than a virus, but 10 times heavier. And it interfered. The numbers, written out plainly, give a sense of the pace: 720 daltons in 1999, 1,600 in 2003, 6,900 in around 2011. And then, 8 years later, the next rung, 25,000 daltons in 2019. From the buckyball to the 2019 record, the mass climbed roughly 35 times in 20 years. 35 times heavier in 2 decades of concentrated effort, which sounds perhaps like reasonable progress. And then you remember what the original molecule weighed, still less than a single small protein, still nothing you could see or touch or hold, and the enormity of the obstacle becomes clearer. The climbers were moving slowly, not from lack of ambition, but because the mountain was extraordinarily steep. Each step required defeating something that grew worse with every atom added, something that sits at the heart of why the quantum world stays hidden from us. That thing is decoherence. Let me try to explain it in a way that might make sense to you as you lie there in the dark, not quite asleep yet, the room settling around you. Imagine you have just written something on a notepad in very light pencil. While you keep the notepad completely enclosed, in the dark, with nothing touching it, the writing stays perfectly clear. But the moment you let a single photon of light bounce off that page, or allow the faintest breath of air to stir across it, even one molecule of air grazing the surface, information leaks out. Whatever was written starts to diffuse into the surroundings. The message doesn't necessarily disappear from the notepad, but its precise form gets shared with the environment, and the more it is shared, the harder it becomes to read the original clearly. If you could somehow recover every particle that touched that notepad and trace every single interaction, you could in principle reconstruct the message. But in practice, the information has simply spread too far, too fast, into too many untrackable places. Decoherence works like that for quantum waves. When a molecule travels through an interferometer in a superposition, taking two paths at once, its quantum waves spread across both arms of the apparatus. The interference pattern exists only as long as no information leaks out about which path the molecule actually took. The moment the molecule interacts with something in its environment, even a single gas molecule drifting past, even a single photon of thermal radiation grazing its surface, the quantum wave stops being a coherent, interfering whole. The environment has, in effect, peaked. It has received a faint message. This molecule was here rather than there. And the moment that message exists anywhere in the world, even encoded in the tiniest vibration of a nearby atom, the interference fringes are gone. The pattern collapses to randomness. The cat is forced to choose. This is the fundamental obstacle for the molecule interferometry experiments. And here is what makes it so punishing as the molecules get heavier and more complex. Every atom you add to the molecule is another handle the environment can grab. A C60 molecule has 60 carbon atoms. It's a small, symmetric, relatively cold object that can drift through a carefully evacuated apparatus without giving itself away too often. But a molecule with 430 atoms or 2,000 atoms is a much larger, more complex, more chemically active entity. It has more surface area, more bonds that can vibrate, more chances to interact with stray gas molecules in the vacuum chamber. Each additional atom is, as the experimenters have put it, a better antenna, more sensitive to the slightest environmental signal, more eager to tell the world where it is. And there is a second problem, which is in some ways even harder to solve. A hot molecule glows. Not in the way that a coal in a fireplace glows. You wouldn't see it with your eyes. But a molecule with any significant internal temperature will emit infrared photons, just as any warm body does. Each one of those photons carries information about the molecule's position and temperature. It is a tiny signal radiated outward into the world. And if even one of those photons escapes the apparatus and is in principle detectable, that is enough. The interference fringes wash away. The molecule has inadvertently measured itself. A warm molecule is its own spy. This is why the experiments are conducted in ultra-high vacuum, pressures so low that the number of gas molecules remaining in the apparatus is reduced to an almost incomprehensible minimum. Fewer air molecules in a cubic centimetre of the vacuum chamber than in the best vacuum that existed anywhere on Earth a century ago. And this is why keeping the molecule's internal temperature under control matters so much. A hot molecule will decohere itself. A cool one has a fighting chance. But, and here the patient genius of the experimenters comes in, you can't simply slow the molecules down to cool them, because slower molecules have lower momentum, and lower momentum means a longer de Broglie wavelength, which should make the wave behavior easier to see, except that slower molecules also spend longer in the apparatus and have more time to decohere. Every parameter you adjust to help you on one side of the problem tends to hurt you on the other. This is the exquisite, frustrating balancing act at the heart of the whole enterprise. And it is why each rung of the ladder took years to reach, and why the gap between 6,900 daltons and 25,000 daltons took 8 years to cross. The machines that made the climb possible were themselves objects of considerable ingenuity. Let me tell you about them, because they are beautiful in their own right. and because understanding them gives you a real sense of what it means to interfere a molecule rather than just gesturing at the idea. The fundamental device behind most of the early records in this field is called a Talbot-Lowe interferometer. The name comes from two different pieces of physics history. Henry Fox Talbot was a 19th-century British scientist who noticed in 1836 that if you placed a diffraction grating in a beam of light, the grating would produce an exact image of itself at certain distances downstream, a self-image conjured from interference, appearing in thin air. It is called the Talbot effect. Now, Louis de Broglie's insight that every particle has a wavelength meant that a beam of molecules should, in principle, be able to produce Talbot self-images too if you arrange the gratings correctly. And Johann Heinrich von Mindler-Lau, separately, had worked out how to make such interference happen even when your beam wasn't perfectly parallel or perfectly monochromatic, even when it was, in a word, messy, and molecule beams are messy. You can't tune a beam of large, complex molecules to travel at a single, precise velocity the way you can tune a laser to a specific wavelength. The molecules emerge from their source at a range of speeds, a spread of momenta, a spread of wavelengths. A classic double slit, which requires a clean, coherent, well-collimated beam, would simply produce a blur. The Talbot-Lowe geometry works around this. Instead of one grating, it uses typically three, arranged in sequence at specific, calculated spacings. The first grating sorts the beam, not perfectly, but enough. The second grating is where the interference actually happens, the wave splitting and going multiple ways at once. The third grating is the detector side analyzer used to sample the resulting interference pattern. What you detect is not the fringe pattern directly, that would be nearly invisible at the scale of these experiments, but rather the variation in how many molecules arrive at each position as you slide the third grating across. And from that variation, you reconstruct what the fringe pattern must have been. It is less like taking a photograph of the wave and more like reading the wave through a series of careful measurements. Indirect, painstaking, and very clever. As the molecules got heavier and stickier, physically adhering to solid gratings rather than passing cleanly through the gaps, the Vienna group and their collaborators developed a more refined version of the device. By the time of the phthalocyanine experiments around 2011 and 2012, they were using a Kapitsa-Dirac-Talbot-Lowe interferometer. The Kapitsa-Dirac part refers to something specific instead of solid nanofabricated gratings with physical bars and gaps, the kind that large molecules could simply crash into and stick. One or more of the gratings was replaced by a standing wave of laser light. A standing wave of laser light is a periodic structure of electromagnetic field, alternating bright and dark fringes, spaced at half the wavelength of the laser, and a molecule passing through that standing wave is diffracted, bent by the light itself, rather than by a physical wall. No solid barrier to stick to, no surface to contaminate, the grating exists as pure, clean, repetitive light. This was a significant advance. It meant the interferometer could work with larger, heavier, more complex molecules that would have been lost to a solid grating. And it meant the team could climb another rung. Quick reminder, after years of lying awake with a racing mind, deep sleep finally became possible. Now learning comes easier, energy is real, and the mind stays sharp. Sleeping like a baby changed everything. If you want the exact system that made this possible, check the link in the pinned comments. But even the Kapitsa-Dirac-Talbot-Lowe design had limits, and those limits led to another machine with another name, OTIMA, the optical time domain ionizing matter wave interferometer. The name is a mouthful, but the idea behind it is elegant enough that it is worth sitting with for a moment. In all the earlier designs, the molecule beam and the gratings were arranged in space. The molecules travelled through one grating, then another, separated by physical distances along the length of the instrument. The timing was implicit. How long it took a molecule to travel from one grating to the next depended on how fast it was moving, which varied across the beam. This was one source of messiness. OTIMA did something different. It replaced the spatial arrangement with a temporal one. Instead of separating the gratings in space, it used pulsed ultraviolet laser gratings fired at precise moments in time. A flash of ultraviolet light at time 0, that's the first grating, creating a periodic pattern of ionization that marks some molecules and lets others pass. A flash at time t later, the second grating, splitting the matter wave. A flash at time 2t, the third grating, the analyzer. The molecules between pulses are free, drifting in vacuum, interacting with nothing. The grating comes to them in time rather than waiting for them in space. This temporal design has a particularly useful property when you are working with very heavy molecules. It means the interference pattern is much less sensitive to the spread of velocities in the beam, because all molecules, fast and slow, experience the same temporal grating structure at the same moments. The velocity spread that made earlier designs messy becomes less damaging, and the ultraviolet pulses can ionize the molecules at precisely defined moments, allowing the detector to know exactly which molecules have passed through all three gratings in the right sequence. OTIMA was designed specifically with the climb in mind. It was designed to go higher on the mass ladder than solid gratings or even the light grating hybrid designs could manage. It was designed for heavier objects, and it sits now in the experimental toolkit of this field as one of the key instruments pointed toward the next frontier. But the headline record from 2019, the 25,000 Dalton oligoporphyrin molecules, the 2,000 atom objects that currently sit at the top of the spatial superposition ladder, was achieved in a different machine. That machine was called the LUMI, the long baseline universal matter wave interferometer. And the L in long baseline is worth pausing on. The LUMI was, physically, a large instrument, about 2 meters of length, not particularly impressive by the standards of a physics laboratory filled with optical tables and refrigeration units, but large for a matter wave interferometer, where the distances between gratings are typically millimeters to tens of centimeters. The longer the baseline, the more time the molecules spend inside the interferometer between gratings. The more time inside, the more any speed differences between molecules can spread the beam, and the larger the spatial separation between the two paths the molecule's wave takes. A longer baseline means a chance to work with heavier, slower molecules that would arrive at a shorter interferometer's detector before the interference pattern could even form. The molecules Yaakov Fein, Markus Arndt, and their colleagues chose for the 2019 experiment were specifically designed, not found in a chemical catalogue. Designed, they are called oligoporphyrins, complex, tailor-made organic molecules built around a chain of porphyrin units. The same family of ring structures that appears in chlorophyll, in the hemoglobin in your blood, in a remarkable variety of biological chemistry. But these were not biological molecules. They were synthesized in the laboratory specifically to be as heavy as possible while remaining stable enough to be evaporated and launched through a matter wave interferometer. and volatile enough not to simply stick to every surface they encountered. The largest of the molecules used in that experiment contained around 2,000 atoms, and their mass exceeded 25,000 daltons. 25 kilodaltons, as chemists would say. In absolute terms, that is roughly 4 times 10 to the negative 23 kilograms. Written out, that is a decimal point, followed by 22 zeros, and then a 4. Fantastically, staggeringly small. But also the heaviest single object ever placed in a demonstrable spatial superposition. 2 paths, 2 places, 1 molecule, simultaneously in the history of physics. The wave that accomplished this is worth thinking about for a moment as you settle a little further into wherever you are. The de Broglie wavelength of those molecules, travelling at the speeds relevant to the experiment, was on the order of tens of femtometers. A femtometer is 10 to the power of negative 15 meters. 1/millionth of a nanometer. Smaller than a proton. Smaller, in fact, than the scale at which protons themselves have structure. The molecule is roughly a nanometer across, the wave that delocalized it, that spread it across 2 distinct paths through the interferometer and demonstrated its quantum nature, was approximately 1,000 times smaller than the molecule itself. The molecule rode a wave tinier than any of its own constituent parts. It was delocalized by something smaller than the ingredients it was built from. This image, this molecule, visible by almost no standard of measurement you could apply in the ordinary world, split and spread across 2 paths by a wave 10 times smaller than a single hydrogen atom, is, I think, one of the more quietly astonishing images that physics has produced in recent decades. Not explosive or dramatic, not accompanied by a flash of light or a trembling of the ground. Just a faint, patient statistical signal emerging over many thousands of molecules, slowly accumulated in a 2-meter machine in a very careful laboratory in Vienna. A signal that said, yes, even this, even 2,000 atoms. The wave is still there. And yet, and this is the part that the careful experimenters were always clear about, and the part that the sleep-deprived popular science articles sometimes obscure, the climb was punishing precisely because decoherence does not rest. Every single one of those 2,000 atoms was another handle for the world to grab. Every vibration inside the molecule, every infrared photon the molecule might radiate from its internal warmth, was a potential spy. The vacuum in the LUMI was maintained at pressures low enough that the chance of a gas molecule colliding with the specimen during its flight was vanishingly small. The molecules were kept as internally cool as the experimental conditions allowed. The whole apparatus was vibration isolated, tucked away from the mechanical noise of the building and the city around it. And even then, the interference contrast, the sharpness of the fringes, how clearly the wave pattern stood out from the background, was not perfect. Real experiments rarely are. The contrast was measured and analyzed and compared against what quantum mechanics predicted, accounting for all the known sources of decoherence, and the agreement was good. The fringe pattern was there, the quantum wave had survived. But the margin was not vast. The world was pressing in from every side, eager to take its peak, and the experimenters were holding it back through the sheer accumulated ingenuity of their apparatus. 35 times heavier than the buckyball. 20 years of climbing, and they reached a molecule you still could not see with the most powerful optical microscope you own, a molecule that would be invisible to you if it landed on your fingernail, a molecule that exists at a scale so far below the threshold of your senses that it might as well be in another dimension. And yet it was in two places at once. Demonstrably, measurably, precisely, not by analogy, not by philosophical sleight of hand, by interference fringes on a detector, fringe positions that only exist if something travelled both paths simultaneously. De Broglie's equation, duc(h)mv, Planck's constant divided by mass times velocity, is the quiet villain of this story and its quiet hero at the same time. The villain because it tells you, with cold mathematical honesty, that every gram you add to your molecule shrinks the wavelength by a proportional amount. And a shorter wavelength is a harder wave to see. The spacing of your interference fringes scales with the wavelength, half the wavelength, half the fringe spacing, twice as hard to measure, twice as demanding on your detector's resolution, twice as easy for any residual decoherence to wash out before you can read it. The equation is what makes the climb so steep. It is why the record rose only 35 times in 20 years, when the instruments improved by far more than 35 times in the same period. But it is also the hero, because it is the guarantee that the wave exists at all. De Broglie's 1924 insight that matter has a wavelength, unconditionally, without exception, is what makes every rung of the ladder possible. The wave is always there, for every mass. You just have to find a machine clever enough to see it before the world covers your eyes. The buckyballs were a beginning. 1,600 daltons a few years later. 6,900 daltons in the phthalocyanine experiments of 2011 and 2012. And then, in 2019, the LUMI and the oligoporphyrins and 25,000 daltons. A ladder with no theoretical ceiling, only a practical one that keeps moving as the instruments improve and the vacuum gets better and the molecules get cleverer. The question that hangs in the warm dark of this room now, the question that should just barely keep you from drifting off for another moment or two, is not just how heavy is the current record. You know that now. You have that number. 25,000 daltons, 2,000 atoms, 4 times 10 to the minus 23 kilograms. The question is, where does it end? Is there a wall somewhere above the current record? A place where, no matter how good your machine, or how hard you work your vacuum pump, or how cleverly you design your molecule, the quantum wave simply cannot survive? A border that is real and fundamental, not just a practical limit we keep pushing outward. Because if such a wall exists, then something must be building it. Something must be causing the collapse, the forced choice, the click of the cat falling decidedly to one side. And there is a very old and very beautiful idea about what that something might be. An idea that involves the most familiar force in your experience, the force that holds you against your bed right now, the force that makes the lamp on your bedside table stay on the table instead of drifting gently toward the ceiling. The force that Isaac Newton watched operate on a falling apple and that Albert Einstein rewrote as the geometry of space-time. Gravity, the idea that gravity might be the thing that ends the quantum story. The thing that makes the cat land, the thing that built the wall we are looking for. It is a serious, carefully worked-out proposal, with equations and predictions and, now, an experimental verdict delivered from deep beneath an Italian mountain. And that is where we will wander next. Into the gravity question. Into the underground laboratory. Into the faint glow that never came, and what its absence means for the border between quantum and everything else. But for now, the ladder. Hold the ladder in your mind as you settle further into the dark. 1999, and a tiny soccer ball of carbon atoms doing something that, in Schrödinger's day, would have seemed utterly impossible. 2003, and a heavier, more complex molecule following it up the first few rungs. 2011, a larger and stranger molecule still, interfered by gratings of pure laser light. 2019, 2,000 atoms of tailored chemistry in a 2-meter machine, splitting across two paths with a wave smaller than anything inside it. And somewhere ahead of all of that, an as-yet unreached rung where the next record waits to be made, where the next experiment is being planned, the next vacuum pump installed, the next molecule designed. Slow, patient, exact, and beautiful in the way that very careful things can be beautiful, the way along. Unhurried conversation at the edge of sleep can be beautiful, where no one is in a hurry and every idea is allowed to arrive at its own pace. Rest in that for a moment. The climbers are still climbing. You are allowed to close your eyes. So, the gravity question. Let's drift into it slowly, the way you might drift toward the edge of a dream, not falling, exactly, just leaning, the ground becoming something softer and more uncertain underfoot. And let's start, as is often the way with the best questions in physics, with something that looks like common sense. You know, by now, that quantum things are strange. Electrons and molecules spreading themselves across multiple paths, leaving interference patterns like ripples from a stone dropped in a still pond. You know that the bigger the object, the harder it gets to see that strangeness, that de Broglie's equation. That one clean fraction, with Planck's constant on top and momentum below, shrinks the wave relentlessly as mass climbs. You know that decoherence is always waiting, the environment pressing in, air molecules and wandering photons nudging a quantum thing out of its beautiful ambiguity and into something that looks like a choice. But here is the question that has genuinely troubled some of the deepest thinkers in physics for decades now. A question that sounds almost too big to take seriously, and yet refuses to go away. What if it isn't just decoherence? What if there is something else, something fundamental, something baked into the fabric of reality itself, that reaches in and stops the quantum world from spilling into the everyday? What if the collapse of a quantum superposition isn't just a practical problem, a matter of keeping the air cold enough and the vacuum tight enough and the vibrations still enough, but a physical law, as real and as non-negotiable as gravity? And in fact, what if it literally is gravity? Stay with that for a moment. Let your eyes rest, wherever you are. Maybe your room is dark now, the last of the evening folded away, and the only sound is something faint and familiar. Let the question just sit there for a breath or two, because it's a serious one, and it deserves that. The idea has a name. Two names, actually, because it was arrived at independently by two physicists working on different sides of the same deep puzzle. The first is Lajos Dissi, a Hungarian theorist who in 1989 proposed that gravitational effects might introduce an irreducible noise into quantum mechanics, a kind of unavoidable jitter in the wave function that grows more powerful the more massive the object involved, until superpositions of large things simply cannot survive. The second is Roger Penrose, the British mathematician and physicist, author of The Road to Reality, among many other books, winner of the Nobel Prize in Physics, a man who has spent decades arguing that our two great theories of the universe, quantum mechanics and general relativity, cannot simply be stitched together without something giving way. And what gives way, in Penrose's view, might be superposition itself. Their proposal is known as the Dissi Penrose model. And the heart of it is beautiful in the way that ideas which connect two unlikely things can be beautiful. Simple, almost. Here is the core of it, spoken slowly, with no rush. When you place an object in a superposition of two locations, say, you manage somehow to hold a small lump of matter so that it exists, genuinely and simultaneously, in two slightly different positions in space. You have also, in a sense, placed its gravitational field in two slightly different configurations at once. Two slightly different patterns of curved spacetime, since mass curves space. And this lump of mass is in two places, so two gentle dimples in the fabric of things are present simultaneously. And Penrose and Dizzy argued that this cannot be stable, that two different gravitational configurations in superposition carry a tension between them. A gravitational self-energy is the technical phrase, usually written E sub g, and that this tension does not wait patiently. It resolves. The superposition decays, and the time it takes to decay, the lifetime of that quantum state, follows a formula, tau equals h bar divided by E sub g. The collapse time tau, in seconds, is Planck's reduced constant divided by that gravitational self-energy. What does this mean in practice? Sit with the arithmetic for a moment, loose and easy. For something tiny, an electron, a small molecule, E sub g is vanishingly small. The self-energy of two almost identical gravitational fields separated by a subatomic distance is almost nothing. And so tau, the lifetime of the superposition, comes out enormous, practically infinite. The electron can hold its quantum strangeness for longer than the age of the universe, on this picture, because gravity barely notices it. It's too small to matter, gravitationally speaking. But scale up. Start adding atoms. Hundreds, thousands, eventually millions. As the object gets heavier and the two possible positions in space become more distinct, E sub g grows. The gravitational self-energy, the tension between two barely different curves in spacetime, increases and tau falls. The collapse time shrinks. The superposition becomes shorter-lived, and for an object the size of a cat, well, the numbers come out so fast that no instrument could ever observe the cat in both states. The collapse, in the Dissy, Penrose picture, happens essentially instantaneously the moment you try to push a cat-sized thing into superposition. Not because of decoherence, not because air molecules are bumping into it, but because gravity itself, the same gravity that keeps you pressed gently into your mattress right now, reaches in and chooses. That is what makes the model so appealing if you're in the mood to be appealed to. It offers a border with a mechanism. Not big things decohere faster, which is true but feels like an engineering problem with a possible solution. Good enough vacuum, cold enough temperatures, but rather big things carry so much gravitational tension when split that reality snaps them back. A genuine wall, a fundamental line. Below it, the quantum world. Above it, the everyday one. And the border is drawn in units of mass and gravitational self-energy, not in units of inconvenience. It is an elegant idea. It connects quantum mechanics to general relativity, two theories that have famously refused to speak the same language for nearly a century. It explains the appearance of classical reality without requiring you to argue about which interpretation of quantum mechanics is correct. It makes a specific, quantitative prediction. It is testable, and here is a good moment to pause gently and say, if you are still with me, wherever you are in the night, and you have been finding this slow walk through physics somehow restful, a like and subscribe on this channel means more than you might think. Small creators like me rely on your support to keep these quiet journeys going. And if you've been here before, thank you. It genuinely matters. Now, back to the mountain. Because the Dicey-Penrose model, for all its elegance, makes a prediction that can be checked. And checking it required going somewhere very particular. Gran Sasso. Say it softly. Gran Sasso. It means big rock in Italian, and it earns the name. Gran Sasso d'Italia is the highest peak in the Apennine Mountains. A long spine of grey limestone running down the centre of Italy, and beneath it, carved through the rock by engineers in the 1980s while building a motorway tunnel, is one of the strangest scientific facilities in the world. The Laboratori Nazionali del Gran Sasso. The Lengs. It sits roughly 1.5 miles underground, beneath 1,400 metres of solid mountain, and it is one of the quietest places on Earth in a very specific sense. Not quiet in the way of a library or a bedroom after midnight. Quiet in the way that matters for particle physics. The rock above shields it from cosmic rays. The constant rain of high-energy particles that arrives from space and passes through ordinary buildings as though they weren't there. At Gran Sasso, that rain slows to a trickle. The mountain is a filter. The laboratory beneath it sees the universe without almost all of that noise, which makes it an ideal place to listen for very faint things. And in the last few years, before the experiment we are about to discuss, a team of physicists, among them Sandro Donardi and Angelo Bassi, and colleagues, set up a detector deep inside that underground hall. A germanium detector. Germanium, the semiconductor element, is useful here because it is sensitive to weak emissions of radiation, X-rays, gamma rays, at energies that would be hard to pick out anywhere noisier. The detector was there, in the dark beneath the mountain, watching. Watching for what? Here is where the Dicey-Penrose model turns from philosophy into experiment. If the collapse of a wave function is caused by gravity, if matter spontaneously localizes itself, snapping from a spread-out quantum state into a definite one, then that process should not be perfectly silent. Energy has to go somewhere. The model predicts that collapsing matter should emit a faint, characteristic radiation, a quiet glow of X-rays. Not much, very faint, but present, and at the parameter values the original, simplest, unmodified version of the Dicey-Penrose model requires that glow should be just barely detectable. If you are deep enough underground to filter out everything else, and patient enough to wait. The experiment ran. The detector watched. The physicists waited, in the dark beneath the mountain, for a signature that would tell them that gravity was quietly dissolving quantum states above them, all over the world, in every atom of every object, in every ordinary room, and leaking just a whisper of that dissolution as radiation. They saw nothing. Or rather, they saw no excess above the background, no glow at the level the simplest Dicey-Penrose model predicted. They published their result in Nature Physics in 2021, a collaboration between groups including Donardi and Bassi, and the conclusion was careful but clear. The simplest parameter-free version of the Dicey-Penrose collapse model is ruled out by this measurement. The whisper it required was not there. Let that settle. The idea that gravity might be the executioner of quantum superpositions, that it might be the thing that collapses the cat's wave function, that draws the line between the quantum world and ours, is not dead. But its plainest, most direct form has now been tested, and it lost. The mountain listened, and nothing spoke back. This is the kind of result that can feel, on first hearing, a little like disappointment. as though the tidy answer, gravity does it, case closed, that's the border, now sleep, has been taken away. But I find, if you sit with it for a moment, that it's actually more interesting than that, much more. Because what it means is that the question is still open, that the wall, if there is one, is not where the simplest map said it was. And in physics, an open question of that depth is not a failure. It is an invitation. Now, the dizzy Penrose model has softened, modified versions, adjusted parameters, weakened assumptions that survive the Gran Sasso result. Gravity collapse is not entirely eliminated as an idea, but its simplest, most natural form, the one where you write down the gravitational self-energy and let the equation predict the collapse time with no free variables to adjust, has been constrained. The data does not support it. And so the field looks around for other possibilities, other ways in which reality might choose, other proposals for where the border comes from. There are two that deserve a quiet mention here because they represent the serious competition, not gravity, but something else entirely. Something built into the structure of quantum mechanics itself, inserted by hand, but with careful intent. The first is called GRU. That stands for Ghirardi, Rimini, Weber, three Italian physicists, Giancarlo Ghirardi, Alberto Rimini, and Tullio Weber, who published a model in 1986 that adds something to the standard equations of quantum mechanics, a small, random, spontaneous collapse. Every particle in the GRU model has a tiny chance each second of having its wave function spontaneously hit. Localized to a point, snapped from spread out to definite, for no reason except that this is, in the model, what particles do. The probability is small, vanishingly small for a single particle. You could wait billions of years and not see it happen. But for large objects, the probabilities add up. Because a large object contains trillions and trillions of particles. And if any one of them is hit, the whole object, linked as it is through quantum correlations, localizes, snaps to a definite state. The more particles, the more chances for a hit per second. The bigger the object, the shorter the superposition's lifetime. Which means, as with Penrose, Dicey, tiny things stay quantum almost forever, and large things become classical almost instantly. The GRU model does not explain why this happens. It does not point to gravity or to any known force. It simply adds the collapse as a new feature of nature, with constants that are chosen to match what we observe, quantum strangeness at small scales, classical definiteness at large ones. It is, in a sense, a map of the border rather than an explanation of it. But it makes predictions, and those predictions can be tested. The second rival is called CSL, Continuous Spontaneous Localization. It's a refinement of GRU developed by Philip Pearl and later worked on by Angelo Bassi and Giancarlo Ghirardi, among others. Where GRU works with sudden, discrete hits, CSL makes the collapse process continuous, a gentle, constant nudging of the wave function toward definiteness. The mathematics is different, and the predictions are slightly different, but the core philosophy is the same. Reality has a built-in tendency to localize. It doesn't need gravity to do it. It does it on its own, quietly, at a rate that scales with size and mass in just the right way to explain the world we see. Both GRU and CSL are what physicists call objective collapse models. Objective, because the collapse is real, physical, happening in the world whether or not anyone is looking. No observer required. The cat dies or survives because of a physical process, not because someone opens the box. That is important. The cat story, you remember, was Schrödinger's way of mocking the idea that observer and observation could matter, and objective collapse models take his side. They say, "You're right, that's absurd, so here is a collapse that happens regardless." What they disagree with Schrödinger about is the conclusion. He thought the absurdity meant quantum mechanics was incomplete, that something was missing from the picture. GRU and CSL agree something is missing, but they've tried to fill the gap. They've added a new physical process, a new term in the equations, a gentle and universal and ever-present nudge toward the definite. And experiments, including searches for the faint radiation that these models also predict, under mountains and in ultra-quiet laboratories, are gradually closing the parameter space around them. The allowed values for the model's constants are shrinking. The region of possibility is getting smaller, not eliminated, not yet, but pressed. Which brings us back to a question that has been waiting at the edge of all of this, the question that sits beneath the gravity proposal and the GRU model and the CSL framework alike, patient and deep and genuinely unresolved. Maybe there is no collapse at all. Stay with that for a breath. This is Wojciech Zurek's territory, and H. Dieter Zay's. Two physicists whose work on decoherence, the process by which a quantum system bleeds information about itself into its environment, becoming entangled with air and light and vibration until its interference terms are completely invisible, changed how physicists think about the quantum to classical transition. Their insight, developed through the 1980s and 90s and refined since, is this. You do not need to add anything to quantum mechanics to explain why the world looks classical. You do not need collapse, objective or gravity-driven. You do not need a new force or a new fundamental process. Decoherence alone, the simple, inevitable entanglement of any large object with its environment, will do it. Think of it this way. Imagine you have a molecule perfectly isolated in a superposition of two positions. Its interference terms are intact. You could, in principle, with the right machine, detect its wave nature. Now let one air molecule drift in and bounce off it. That air molecule now has become entangled with the original molecule. It carries information, not perfect, not detailed, but some, about where the original molecule was. The original molecule's interference terms, its quantum phase relationships, are now partly shared with the air molecule. And if you then measure only the original molecule, tracing over the air molecule as you must, those interference terms look washed out. The quantum pattern has leaked into the environment, and you can't get it back without measuring everything. The original molecule and the air molecule, and everything the air molecule subsequently bumped into, down through an ever-growing tree of entanglement. For a molecule in ultra-high vacuum, this process is slow enough to manage. That's why the Vienna experiments work. But for a dust grain in ordinary air, the decoherence is catastrophic. Z calculated, and the numbers are genuinely staggering, that a dust grain in air loses its quantum coherence in something like 10 to the minus 31 seconds. That is not a small number with a minus sign in front. It is almost impossibly fast. Faster than light crosses a proton. The quantum pattern for anything that size in ordinary conditions is simply gone before you can think to measure it. And here is the deep thing, the thing that makes decoherence philosophically charged even if it sounds like engineering. Zurek and Zay's picture says that the wave function never really collapses, it just spreads. The cat is still, in some sense, in a superposition, but a superposition so entangled with every atom in the laboratory, every photon in the room, every vibration in the bench and the air and the floor, that no interference pattern is recoverable. The quantum state exists. It has just distributed itself so thoroughly across the world that it looks, to anyone inside the world, completely classical. This is sometimes called quantum Darwinism, the term Zurek uses for the way that information about a quantum system gets copied redundantly into the environment. Many copies, many photons, carrying the same news about which path the object took, so that any observer anywhere can check and they all agree. The classical world is not a special place separate from the quantum one. It is the quantum world, viewed from the inside when the pattern is too spread to see. Which means the border between quantum and everyday might not be a wall at all. Might not be a fundamental line drawn by gravity or by some new collapse law. Might be more like a horizon. Not a thing in itself, but a limit on what we can see from where we are standing. The quantum world does not end at large scales. We simply cannot reconstruct it. The coherence is there somewhere, woven into the fabric of everything. We've just lost the thread. And the whole enterprise of molecule interferometry, the whole Vienna program from buckyballs to oligoporphyrins, is in this sense an experiment not just in how big a quantum object can be, but in how far back that horizon can be pushed. Every time Markus Arndt and his colleagues build a heavier molecule and send it through LUMI and recover an interference pattern, they are demonstrating that the horizon is further than we thought, that the world stays quantum a little longer than the last time we checked. The experiment is the border, and the border is moving. Now there is one more piece to this part of the story, one more proposal that sits at the very edge of what has been attempted and what remains to be done, and it is the one that makes even careful physicists sit up slightly straighter when they discuss it. If you put a tiny mass into a superposition of two positions, not just as a matter wave pattern, but a real, physical, spatially separated state, its gravitational field is also, presumably, in superposition. Two slightly different curves in spacetime, both real, both present. And the question that follows from this is one that nobody has yet been able to answer experimentally. Because the experiment is still beyond our reach, but which theorists have thought about very carefully. Could two such masses, each in its own gravitational superposition, become entangled with each other, not through electromagnetism, not through any known quantum force, but purely through their gravitational interaction? This is the idea behind what are called gravitationally induced entanglement tests. Sandro Bose, Chiara Marletto and Vlatko Vedral, and independently Carsten Marletto and Vedral, proposed that if you could prepare two small masses in superpositions of nearby positions and let them interact only gravitationally, then measure whether they have become quantum mechanically entangled, you would learn something extraordinary. If they are entangled, then the gravitational interaction that produced the entanglement must itself have been quantum in nature. Because entanglement cannot be produced by a purely classical intermediary. If gravity entangles them, gravity is quantum. This would be the first direct experimental evidence that gravity, the oldest and most familiar force, the one that bends starlight and keeps you in your bed, is not exempt from the quantum world. No one has done this experiment yet. The masses involved would need to be small enough to maintain quantum coherence, long enough to interact and show entanglement, and yet massive enough to have a measurable gravitational effect on each other. That combination of requirements sits just beyond what current technology can manage. But it sits close enough that laboratories around the world are working toward it. The Bose-Marletto-Vedral test, as it has come to be called, is one of the deep prizes of experimental physics in the coming decades. And alongside it, the dream of space. of taking the whole problem off the Earth, away from the seismic vibrations and the residual gas and the thermal noise that make decoherence so hard to beat on the ground. The macro proposal, the macroscopic quantum resonators mission, a concept developed for the European Space Agency, imagines doing matter-wave interferometry in orbit in the long, quiet, free fall of space, with nanoparticles of 100 million to 10 billion atomic mass units. Far beyond anything LUMI has achieved, objects at the edge of what you might begin to see under a powerful optical microscope. In the near-perfect vacuum and near-perfect cold of deep space, where decoherence is almost absent, and the only remaining question is whether some fundamental collapse law, gravity, CSL, or something not yet imagined, reaches up and intervenes. Macro has not launched. It remains a proposal, a careful and beautiful one, waiting for the moment when funding and political will and technology align. But it represents the direction, the shape of the question, up and out, into the cold, where the only noise left is the noise that comes from reality itself. And so the question of where the border lies between the quantum and the everyday has become, in a very real sense, an experimental program with a ladder and a scoreboard and a dream of space. Not a philosophical debate to be settled by argument, but a series of experiments to be performed one by one, with increasingly heavy objects, in increasingly quiet conditions, until either the interference pattern finally fails and we find the wall, or it doesn't, and we find that the wall was always just the horizon. Somewhere along that program, something will give way. Either decoherence will always win before any fundamental collapse has a chance to act, in which case the border is practical, not fundamental, and we are simply waiting for better technology. Or an experiment will find that the interference pattern disappears faster than decoherence alone can explain, and the extra disappearance will point towards something new. Gravity, spontaneous collapse, something not yet named. That is the open heart of this, the genuinely unresolved center of the whole story. And it is a beautiful thing to hold as you lie in the dark, if you can feel it as it is, not as a problem, not as an anxiety, but as a question, still warm and living, still being asked, still being patiently pursued by people in basements and mountaintops and orbit dreaming offices. The ladder is still being climbed, the mountain is still being listened to. The vacuum pumps are still running, somewhere in Vienna, and somewhere else, and somewhere after that. Patient, exact, unhurried. The way the best science always is. The way the best questions always wait, not demanding an answer tonight. Content to keep you company in the dark while you drift slowly towards sleep. Knowing they'll still be there in the morning. Still curious, still open, still full of whatever it is that makes the universe worth wondering about. And there is another branch of the climb, a different kind of cat. Because the molecule experiments, the buckyballs, the oligoporphyrins, the LUMI and its femtometer waves, are asking one specific question: can an object be in two different places at once? Can it travel two paths and interfere with itself? That is spatial superposition, and it is exactly what the 2019 Vienna result achieved. But there is a second kind of two states at once, and it involves objects far heavier than any molecule that has yet been fired through a grating. Objects that in one case you could almost see with your own eyes. Let me tell you about a drum. Not a drum in any poetic sense. A real, physical, mechanical drum, a tiny sliver of aluminum nitride crystal, roughly as wide as a few human hairs laid side by side, suspended like a trampoline on a chip of silicon about the size of your thumbnail. A genuine physical object you could hold on a fingertip, in principle, though you would ruin it immediately with the warmth of your skin. A drum that sits in a refrigerator cooled to within a fraction of a degree above absolute zero. Because at those temperatures that make deep space feel tropical, the thermal noise that normally keeps everything jittering has been almost entirely drained away. In 2010, Andrew Cleland and John Martinis, working at the University of California, Santa Barbara, did something with that drum that had never been done before. They coupled it, gently, carefully, using the tools of superconducting circuitry, to a quantum device. A superconducting qubit, which is essentially a tiny electrical circuit cooled until it obeys quantum rules outright, until it is comfortable in a superposition of two electrical states. The qubit is a quantum object, well established, well studied. That part was not new. What Cleland and Martinis did was reach across the divide between the quantum world and the mechanical world. They let the qubit talk to the drum, and through that conversation they placed the drum itself, the physical, vibrating, crystalline, almost visible drum, into a superposition of two states at once. Not two positions, two modes of vibration. One state, the drum sitting perfectly still, in its lowest possible energy level, its quantum ground state, not vibrating at all. Zero phonons, as physicists say, phonons being the quantum packets of vibration, the way photons are packets of light, and in the ground state there are none. The drum is as quiet as it can possibly be. The other state, the drum vibrating with exactly one quantum of vibrational energy. One phonon, the tiniest possible ring, a single quantum unit of mechanical motion, both at once, still and ringing, simultaneously in the same drum. In the same moment, that superposition, the quantum drum in both its quietest and its gentlest ring at the same time, is what Cleland and Martinis demonstrated, and Science magazine named it the breakthrough of the year for 2010. Not because superconducting qubits were new, not because cooling things to near absolute zero was new, but because the line that everyone had quietly assumed, the line between quantum objects and mechanical objects, between the domain of qubits and the domain of drums you could, in principle, almost see, turned out not to exist in any fundamental way. The drum played by quantum rules, it went into two states at once, and the superposition was real and measurable. Now, you might reasonably ask, how big is a few hair widths? And the honest answer is, not big, not cat big, not even dust mote big, not really, but roughly, and this is the number that makes physicists sit up, on the order of 1 trillion atoms. 1 trillion. That is roughly 10 to the 12th atoms in the object, give or take, depending on how you count. And that is vastly, staggeringly larger than a 2,000-atom oligoporphyrin molecule. The drum is in a completely different size class. It is approaching the threshold where, under the right lighting, you could point a decent optical microscope at it and see something, which is why it matters so much. The molecule experiments ask how far we can push spatial superposition, two places at once. The drum experiment asked something slightly different. How far up the size ladder can quantum mechanical behavior persist? Can a genuinely mechanical object, something you might touch if not for its fragility, live in two energy states at the same time? The answer, in 2010, was yes. Conditionally, provisionally, under extreme cold and extreme care. But yes. And here is the thing about those two branches of the climb, the molecule experiments and the mechanical resonator experiments, they are not competing. They are circling the same mountain from different sides. One group is pushing the mass record for spatial superposition, molecule by molecule. Another group is cooling and coupling and coupling and cooling, trying to get genuinely macroscopic mechanical objects, things that brush against visibility, to live in quantum states long enough to study. Both are asking the same deep question: where does it stop? A few years after the quantum drum, the climbing continued. Shifted location, shifted approach, kept the same patient spirit. In Vienna, always Vienna it seems, always that particular tradition of careful experiment stretching back through the decades, a group led by Markus Arndt was working on something that required not a chip, not a circuit, but a bead of glass. A silica nanoparticle, roughly 100 nanometers across, which is to say, much too small to see directly with the eye, but visible under a good enough microscope, a smooth, almost spherical little bead of amorphous silicon dioxide, the same stuff as sand, really, polished at the nanoscale, and they were using lasers to hold it in mid-air. This is called optical levitation, and it is exactly as beautiful as it sounds. A tightly focused laser beam creates a tiny trap, a kind of optical bowl, and the nanoparticle sits inside the bowl, held there by the pressure of the light itself, floating in vacuum, touching nothing. No surface, no substrate, no contamination from a chip or a mount. Just the bead, suspended in laser light, in a chamber from which almost all the air has been pumped away. The goal was to cool the bead's motion, its jiggling, its tiny random bouncing around inside the trap, down to the quantum ground state. To drain away all the thermal noise until the center of mass motion of this little glass sphere obeyed quantum mechanics directly. And in 2020, Aspelmeyer's group, using a technique called cavity optomechanics, in which the laser light inside a carefully tuned optical cavity both traps and continuously monitors the particle's motion, feeding back corrections to squeeze out the thermal jitter, they achieved it. The nanoparticle's center of mass motion was cooled below 1 phonon of energy, below the quantum ground state threshold. 10 to the 8, 10 to the 9 atoms, hundreds of millions of atoms, perhaps a billion or so, floating in vacuum, cooled by light, brought to their quantum quietest. It is not yet in a spatial superposition, not yet two places at once. The ground state is a necessary step on the way to that, not the destination itself. But it is the launch pad. Once the center of mass is in its ground state, once the thermal noise is gone, you can, in principle, begin to coherently split it, begin to push it into a superposition of being slightly here and slightly there, simultaneously, and see whether interference appears before decoherence destroys it. That experiment has not yet been done with a levitated nanoparticle. But the platform is ready. The ground state has been reached. The next step is being designed. And in 2021, there were further steps in the mechanical direction. Other groups, working with aluminum membranes, stretched drumheads of metal at the micro scale, demonstrated entanglement between two such membranes. Two separate mechanical objects, bigger than any molecule interferometry has touched, each in a quantum state. Their states correlated in the way that entangled quantum objects are, measure one, and you instantly constrain what you will find in the other. The mechanical world was no longer just barely quantum. It was exhibiting the deep quantum correlations that Einstein once called, with a mixture of awe and distaste, spooky action at a distance. So the picture, if you hold it at arm's length and let it blur a little into its shape, is this: from many directions, many labs, many approaches, the frontier of the quantum world is being pushed outward. Molecules interfering in space, drums in superpositions of vibration. nanoparticles cooled to the ground state, membranes entangled with each other. Every experiment a little heavier, a little larger, a little more macroscopic than what came before. And at some point, someone needed to figure out how to compare them. Because a molecule in two positions is not quite the same achievement as a drum in two energy states, and a nanoparticle in its ground state is not quite the same as either. How do you put all of these on the same ladder? How do you say which step is higher? That is the question that Stefan Nimrichter and Klaus Hornberger sat down to answer in 2013, and the answer they came up with is a single number: the macroscopicity parameter. The idea is elegant in the way that good physics ideas are. It does not feel, once you understand it, like it required any cleverness at all, just the right kind of clarity. Nimrichter and Hornberger defined macroscopicity as a measure of how well a given experiment rules out certain classes of modifications to quantum mechanics. Not all modifications, not some particular favorite theory, but a broad family of alternatives in which superpositions of large things are suppressed relative to superpositions of small things. The bigger the object that was demonstrably in two states, and the longer the superposition lasted, and the more genuinely distinct the two states were from each other, the higher the value. The more constraining the experiment is on the broad class of quantum mechanics breaks down for big things theories. It turns out that when you put the molecule experiments and the mechanical resonator experiments on this common scale, they are not so far apart as you might think. The mass numbers are wildly different: 1 trillion atoms for the drum versus 2,000 for the molecule, but the superpositions in the molecule experiments are spatial and they last for longer. And the two paths are genuinely different positions in space, not just different energy levels of the same position. The macroscopicity parameter is not just mass, it is a combination of mass, coherence time, and how distinct the two states are. This is important because it means there is no single magic threshold, there is no weight at which everything suddenly turns classical. There is a continuous scoreboard climbing in, and every new experiment adds to it. Every new molecule sent through LUMI, every drum cooled a little further, every nanoparticle nudged toward its first spatial superposition, all of them register on the same scale. All of them answer the same question by another increment. The race has a scoreboard, and the scoreboard has a number, and the number keeps going up. Where is it going? This is where the frontier opens, and where the more speculative part of the climb begins. Not speculative in the sense of being unreliable, but speculative in the sense of being not yet done. Proposed, planned, designed, longed for. One of the most beautiful proposals is called macro. Matter wave quantum mechanics, research and objectives, a mission concept developed by a group of European physicists and proposed to the European Space Agency. The idea, stated simply, is to take the levitated nanoparticle experiment off the surface of the Earth entirely. Launch it into orbit. Why? Because the barriers that prevent a bigger spatial superposition on Earth are not fundamental. They are practical. Gravity pulls on the nanoparticle while you are trying to split it into two coherent paths. You have to work against that pull, and it limits how long the superposition can be maintained. Vibration from the ground. Traffic. People walking. The endless low hum of a city that never quite stops rattles the experiment and introduces decoherence. The vacuum on Earth can only be made so good because the chamber walls themselves are constantly breathing out stray gas molecules. Temperature can only be lowered so far without heroic infrastructure. In orbit, you get, for free, a long free fall. The spacecraft is falling around the Earth, and so is everything inside it, and in that endless fall there is no effective gravity to fight. The nanoparticle can drift in its superposition for seconds rather than fractions of a second, and seconds, in the world of matter-wave interferometry, is an extraordinary luxury. The vacuum in space is better than any laboratory can achieve on the ground. The thermal environment is quiet and stable. With those conditions, Macro's proponents calculate that it would be possible to put a nanoparticle of around 100 million to 10 billion atomic mass units into a genuine spatial superposition, two clearly distinct positions at the same time. That is roughly 10 to the 8 to 10 to the 10 atoms. Not quite visible, but closer. Much closer than anything that has been done on the ground with interferometry. And the spatial separation between the two arms of the superposition could be genuinely macroscopic by quantum standards, not a femtometer, not a picometer, but potentially something on the nanometer to micron scale. Two positions that are, while still tiny by everyday standards, enormous by the standards of what quantum mechanics has previously been asked to maintain. Macro has not yet been approved for flight. It remains a proposal, a blueprint, a drawing of what is possible. But the physics behind it is sound, and the engineering is within reach, and somewhere in the future no one knows when exactly, because space missions are patient things, slow-moving things. Things that spend years being studied before they are ever built. It may fly. And if it does, the results will be direct evidence about where the real border is. If the nanoparticle in orbit interferes cleanly at that size, it means no collapse mechanism has intervened. The wave function survived, delocalized across two positions for the full duration of the experiment. Decoherence is manageable in that environment, and whatever spontaneous collapse models predict, reality did not comply. That would push the frontier further. That would raise by an enormous stride. And if the interference pattern is missing, or degraded beyond what decoherence alone can explain, well, that would be the wall. That would be where something new enters the picture. But there is another experiment lurking in the future, one even more tantalizing, one that opens a completely different door. And it goes by the names of three physicists, Sugato Bose, Vlatko Vedral, and Chiara Marletto, alongside work by Anupam Mazumdar. The idea is called, depending on who is explaining it, either gravitationally induced entanglement or the Bose-Marletto-Vedral test. Here is the thought at its heart. Take two tiny masses. Not atoms, not molecules, but small objects, nanoparticles or something close. Put each one into a spatial superposition independently. Let them float, each in its own quantum fog of two places at once, near each other but not touching, not connected by any cable or field or electromagnetic interaction that you have arranged. And wait. Just wait. Because those two masses still feel gravity, they still attract each other. Gravity reaches across the gap between them, gently, invisibly, and the question is, if gravity mediates an interaction between two quantum objects, two objects each in superpositions, will the two superpositions become entangled through that gravitational interaction? Entangled in the quantum sense. Correlated in the deep way, so that measuring one of them instantly constrains what you will find in the other, in a way that cannot be explained by any classical signal passing between them, only by the quantum correlations gravity has woven. If you saw that, if the two masses became gravitationally entangled, it would be a sign, a strong sign. It would mean that gravity itself, the force that holds planets in orbit and keeps your feet on the floor and curves the paths of light around stars, is quantum mechanical. that gravity can carry quantum information. That it is not merely a smooth classical field draped over a quantum world, but is itself made of the same strange, superposition-bearing, interference-prone stuff as everything else. This is one of the most profound open questions in physics. Whether gravity is quantum. Whether general relativity, which describes gravity so beautifully in the large, and quantum mechanics, which describes everything else so beautifully in the small, are ultimately reconcilable in a single framework, or whether one of them needs to give way. That question is, in principle, 400 kilometers above your head, waiting to be tested in an orbit that no experiment has yet achieved. No one has done this experiment. It is technically ferocious. The masses need to be isolated almost perfectly from all other forces. The superpositions need to be large enough and clean enough that any gravitational entanglement would be detectable above the noise. The required conditions push to the very edge of what is imaginable with near-future technology. But they do not exceed it. The physics works. The math holds. The experiment is, in principle, performable, and if it ever is performed, and if the entanglement appears, it will be among the most important experimental results in the history of science. Not just important for quantum mechanics, important for our understanding of gravity, important for whatever the final unified theory of physics turns out to be. A 2,000-atom oligoporphyrin molecule sent through a pair of laser gratings in Vienna has, by a long chain of patient steps, led to a question this deep. Schrödinger wrote his cat story to make a point about absurdity. He could not have imagined where the absurdity would lead. Now, before we come to the end of this long, slow journey, before we let the story rest and let you drift, if you haven't already, there is one more thing that I want to give you. Not a fact, exactly, more of a proportion. The heaviest object ever placed into a genuine spatial superposition, the oligoporphyrin molecule, the record holder, the 2019 result from Yaakov Fein and Markus Arndt and their colleagues in Vienna, published in Nature Physics, has a mass of roughly 25,000 daltons. 25 keda, approximately 4 times 10 to the minus 23 kilograms. About 2,000 atoms, and a common housefly has a mass of roughly 12 milligrams, 12 thousandths of a gram. The ratio between the two, between the record-holding quantum molecule and the fly, is approximately 10 to the 22. 10,000 billion. 10 followed by 22 zeros. The most macroscopic quantum object ever made is still, by any measure that your body can feel, unimaginably small. Not almost small. Not slightly small. Absurdly, staggeringly, humblingly small. If you were to scale the gap between the record molecule and a fly the same way you might scale up a single bacterium to the size of the Earth, you would still not have crossed the full distance. The quantum world, even at its current frontier, is not threatening your breakfast. The interference patterns, the superpositions, the femtometer wavelengths, all of it is tucked away in a regime so far below the threshold of your senses that your coffee mug and your blanket and your lamp and the ceiling above you are as safely classical as they have ever been. And that is not a disappointment. That is, if you let it be, a kind of relief, and also a kind of awe. Because here is what it means. It means that the quantum world is real, demonstrated, measured, confirmed in more ways than anyone can easily count, and it is also, for now, exquisitely, precisely contained. The border is not a wall someone built. It is not a rule someone imposed. It is the accumulated weight of atoms, the growing surface area available for the environment to brush against. The increasing number of ways a large object can reveal its own position without anyone asking. The border is practical. It is a fact about decoherence, about vacuum, about temperature, about the punishing exponential cost of adding atoms to a superposition. And it is a fact that we are, right now, alive at the moment when human beings are beginning to push that border, molecule by molecule, phonon by phonon, femtometer by femtometer. We are, in other words, in the middle of the story. Not at the beginning, where the cat was a joke and the electron a mystery. Not at the end, where perhaps a nanoparticle floats in orbit and two masses entangle through gravity and the last question is answered. We are in the middle, which is exactly where the most interesting stories always are. The part where enough has been found to know what the next question is, but not enough has been found to answer it. The part where the machines are running and the papers are being written, and somewhere in Vienna the vacuum pumps are still going. Patient and steady, in the small hours of a morning most of the world is sleeping through. You are, wherever you are listening from tonight, part of the same universe that contains those machines. The same atoms that Arndt and Zeilinger coaxed into interference are the same kind of atoms that make up the bones of your hands and the fluid in your inner ear and the neurons that are, even now, gently losing their grip on wakefulness. Your matter is quantum matter. Every particle in you has a de Broglie wavelength, checks h divided by MeV, though the wavelength is so small, your momentum so large. Your mass so many orders of magnitude beyond the frontier that it will never, under any conditions you will encounter, produce an interference pattern. You are too warm, too heavy, too richly entangled with everything around you. But the quantum rules still hold. They hold all the way down, at every scale, in every atom of you. They are not switched off at the biological threshold. They are simply, beautifully, hidden by decoherence, by the accumulated thermal warmth of a living body, by the 10,000 ways the air and the light and the chemical bath of your cells are constantly brushing against every particle and saying, I know where you are. No superposition survives that. But the rules are there, underneath, always somewhere in the planning stages of future experiments, in the notebooks and preprints and grant proposals of people who will spend the next 20 years of their lives pushing the frontier one careful step at a time, is a question you have carried with you through this whole quiet journey. Not the question about molecules, not the question about drums, not even the question about gravity and Gran Sasso. The oldest question. The one Schrödinger meant as a joke in 1935, the one he wrote down in Die Naturwissenschaften to show how ridiculous it was to take quantum mechanics seriously at the macroscopic scale. The one he was sure had an obvious answer. Where is the border? And the honest answer, the only honest answer the science can give you right now, in the middle of the story, with the record at 25 kDa and the proposals for space missions still on paper, and the gravity collapse model freshly ruled out in its plainest form under an Italian mountain, the honest answer is, we don't know exactly. We know it's somewhere above 25,000 daltons and below a fly. We know it might not be a sharp line at all, but a gradient, a fog, a zone where quantum and classical blur into each other, and only the impracticality of maintaining coherence defines the border rather than any fundamental law. We know that decoherence is almost certainly the dominant story. But we do not know whether there is also a true collapse, a physical mechanism, something that happens to the wave function in reality and not merely in the eye of the environment. We are testing that. We are looking. We have ruled some things out. The question is alive. The search is ongoing. The answer, when it comes, will be one of the most beautiful and strange things ever discovered. And now, I think, is a good time to rest. You've come a long way in the dark tonight. From the cool corridors of the University of Vienna, where a 2,000-atom molecule was threaded through a machine 2 meters long and made to travel 2 paths at once, the heaviest thing ever caught in 2 places simultaneously. Through the history of the climb, the buckyball in 1999, the fluorofullerene, the phthalocyanine derivatives, the slow accretion of atoms across 20 years, and a 35-fold gain in mass. Through the machines, the Talbot, Lau gratings and the Ottimer interferometer, and the long baseline universal matter wave interferometer. Through the femtometer wavelength, that image, the wave smaller than a proton, smaller than 1,000 protons. The extraordinary counterintuitive fact that the wave that split the molecule was far tinier than the molecule itself. Through the gravity question and its strange conclusion, physicists descending beneath the Gran Sasso mountain with a germanium detector, listening for the spontaneous glow that the simplest Dissy Penrose collapse model said must be there, and hearing nothing. The model in its plainest form ruled out. Gravity not yet acquitted, but not yet convicted either. Through the other kind of cat, Andrew Cleland and John Martinis in Santa Barbara in 2010, placing a crystalline drum with 1 trillion atoms into a superposition of perfectly still and gently ringing at the same time. The science breakthrough of the year. The mechanical world obeying quantum rules, and then Markus Arndt in Vienna again, levitating a silica bead in laser light and cooling its motion, hundreds of millions of atoms below the quantum ground state in 2020, the launching platform for the spatial superpositions that have not yet been achieved, but are within reach. The entangled aluminum membranes, the scoreboard, the macroscopicity parameter, the single number that lets all these different experiments compare their achievements and climb the same ladder. And through the horizon, a space mission dreaming of orbit and nanoparticles in long free fall. 2 tiny masses, perhaps one day floating near each other in the vacuum of space, their wave functions spreading, their gravitational attraction threading between them, waiting to see if that attraction will weave them into quantum entanglement. And if it does, whether it will tell us that gravity itself is quantum. Whether the oldest question in the unification of physics might be answered by the gentlest possible experiment. 2 small things, touching each other only through the curve of space-time, asking whether the curve carries quantum information, and through the scale, the humbling, steadying, reassuring scale. 25 kday against 12 milligrams, 10 to the 22 between the record and the fly. The world you live in is not threatened. The cup on your nightstand is not uncertain. The walls of your room are not in superposition. The quantum world is real, and it is small, and it is beautiful, and it is nowhere near your blanket. And yet, here is the quiet thing to carry into sleep. You are made of it. Every quark, every electron, every nucleus in every atom of your body is playing by quantum rules right now, this moment, as you drift. The rules do not stop at the cellular membrane. They go all the way down. The appearance of solidity, of definite position, of a world that chooses one thing at a time, all of that is real. But it is not the bottom. The bottom is weirder. The bottom is a place where a molecule with 2,000 atoms can be in 2 places at once, ridden on a wave smaller than a proton, and arrive on a detector screen as a single certain point that is one node of an interference pattern no single path could have made. You are not separate from that. You are downstream of it. You are, in the most literal physical sense, the stable and classical and beautifully decoherent outcome of quantum rules that go all the way back to the beginning of everything. That is a good thing to hold as the lamp dims and the thoughts loosen and the thinking softens at the edges. If you are still awake and you have found something in this journey worth staying for, a like and a subscribe mean more than I can easily say. Small channels like this one depend on that support to keep the slow journeys coming. And if you are somewhere near sleep or already past it, that is exactly right. That is exactly what this was for. The 25,000 Dalton molecule is still smaller than a housefly by 10 to the 22. The border is still somewhere out there, unmapped, patient, the vacuum pumps are still running, the questions are still open, still warm, still curious, and they will wait. They have been waiting since 1935, since 1924, since the very first physicist looked at a glowing coal and realized the numbers would not work and the world was stranger than anyone had suspected. They will keep until morning. They always do. Wherever you were listening from tonight, I hope the journey was easy on you. I hope the ideas came gently and left a little light behind them. I hope you find what you came here for. Sleep well, fellow voyager. The next journey keeps until you wake.